Now coming to the next, binomial expansion. Now a binomial is basically two terms. So when we are trying to raise a binomial such as a plus b to any power, for example 2, we can write it as a square plus 2ab plus b square. However, when the power increases, like such as 3 or 4 or 5, this process becomes very complex. Now the binomial expansion is very helpful to basically simplify the process when you're raising a binomial to a very high power or even a small power like 5 or 6. Now let n be the power you're raising it to. The expansion will have n plus 1 terms. For example, if you're raising it to 5, then the expansion will have 6 terms. Now the Pascal's triangle is very helpful in finding the coefficients. Now in binomial expansion, you have to make use of combination, which is basically n factorial divided by r factorial into n minus r factorial. However, the Pascal triangle basically gives you the combination for each and every term, making it a shortcut which is very helpful. Now you can use the binomial theorem to basically find the coefficient of the exact term. For example, if I'm doing an expansion and I want basically the coefficient of the x squared term, I can use the binomial expansion to find the coefficient of that exact term instead of expanding it completely. Giving it back to Agnish.
To conclude this segment on the high school tips and tricks, I'll be talking to you about trigonometric tricks and the usage of complex numbers in these subject questions. So beginning with complex numbers and forms. So as you may know, during the discovery of cubic polynomials and when mathematicians were trying to find their solution, that's how imaginary numbers were invented. The square root of a negative was necessary, and this was never thought possible before. But eventually, when they assumed it was true by giving square root of -1 the value I, they eventually cancelled out and provided real usable solutions. Now what you need to know is, in polynomials, like he said, the maximum number of solutions, the real solutions, cannot exceed the degree of the polynomial. So if I have a quintic polynomial which is degree 5, it can't have more than 5 real solutions. But the truth is, every polynomial has the same number of solutions as its degree. The only thing is, some of them are complex and some of them are simple, which is the real solutions. For example, x squared plus 1 equals 0. So if I solve that, I get x is equal to plus or minus square root of negative 1, so it's plus or minus square root of I. So it does indeed have two solutions like other quadratics, but the only thing is they are complex, not real. So the use of complex numbers is very prevalent in, for example, vectors, because when you put them in Cartesian form, which is you have a plus bi, where I is the imaginary number and a and b are coefficients. In that case, you are separating them, you are preventing these two components from interacting, which is the equivalent of having an x and y component, or an I hat and j hat component, or x hat and y hat component, whatever notation that you're used to. So this is essentially what vectors come from. You have different components. You have maybe 3x hat plus 4y hat plus 5z hat, or something like that, whatever number of dimensions you have, x, y, z. But what you're affirming that these three dimensions can't interact by simple addition, unless you're squaring or multiplying them. As such, you're defining each component, each dimension, to be a separate entity in its own right. And again, since this is a vector, those coefficients 3, 4, 5 can represent a force, a velocity, a position, anything that you want really. It's just an arrow that points in space. And the Cartesian form of imaginary numbers, along with various tricks like finding the conjugate, using it to multiplying with counter square roots, or various things like this, allow us to take vectors and their usability to the next level. So they are quite useful in physics. Eventually, when you progress to higher topics, especially the Schrodinger's equation, which does have an imaginary term present in it, specifically I times h bar. Now that's very useful because the solution, the complex solution to the Schrodinger equation actually needs this I, and even the real ones in fact. The next form you need to know is Euler's form, and it's connected to the cis theta form. This is based on Euler's identity. E raised to I times theta is equal to cos theta plus I sin theta. The proof for this may actually surprise you with how simple it is. It's simply from deriving the Taylor series, as you know, of this of e raised to I theta and cos theta plus I sin theta separately. When you add them up, they have the same Taylor series, and hence this proof is true. And this is what gives us the definition of hyperbolic trigonometric functions as well. So you can interconvert between Euler's form and cis form, and you can also interconvert between Cartesian form and these two forms by basically taking the identities r is equal to under root a square plus b square, and theta is equal to tan inverse b over a. Again, all of these formulas are just for your reference. We have linked them in the transcript, and the fact is that seriously, all of these formulas we have linked these formulas in the transcript for your reference. I'm just saying them now for your convenience, so you can link them later. And finally, like I said, there are many interesting properties which in imaginary numbers and complex numbers, which help you find the roots of a polynomial. And often without these, it would be impossible to evaluate all the polynomials. So yeah, they're quite crucial, and whether or not there's direct application is very good to know them. Finally, we'll be looking at trigonometric tricks. Some things you should know about are compound angle formulas, which are like sine of a plus b, cos of a plus b, tan of a plus b, and so on and so forth. It also helps to know the inverses of these, which tend to be like sine inverse a plus sine inverse b, or less frequently sine inverse of a plus b. And you just derive them in forms of simpler sines and coses, or sine inverses and cos inverses. These are very helpful for proofs which involve more than one angle. And as you know, geometry is a very important part of both extended physics and chemistry problems. So these are useful. Then going on an extension from these, you have double and triple angle identities, laws of sines and cosines, laws of tangent, which you should familiarize yourself with, trigonometric substitution, which comes in calculus, which is connected to the reverse U substitution that I mentioned earlier. And finally, there's something called phase angle compounding, which is when you have the sum of a sine and cosine, you combine them into one term. You combine them into either one sine or one cosine. And that's very helpful because one prevalent example is in damped oscillators, which also have complex numbers by the way. Damped oscillators are typically a waveform composed of many different simultaneous waves, which is also true for standing waves and resonance. So when you combine them into one sine or cosine, they're very easy to model. You can identify their properties quickly, and you can answer questions about them very quickly. And also it improves your own understanding. Another application is, of course, in Fourier series, which are also a combination of multiple waveforms. But anyway, that's a lot of details from us. We don't want to overburden you. The transcript is structured in the same way as the episode, so you can refer to every point that we said in a manner that's convenient. And yeah, with that, we wrap up the high school trick section.
Thank you all. Bye.
Bye.